everyone. Welcome to the latest installment of our new editorial webinar series, Coffee Talk. Each hour-long information-packed episode curated by our editors features the insights and observations of an independent expert on a wide range of tech industry topics. Many thanks to the underwriting sponsor of this episode, Cloud and DevOps infrastructure automation provider Quali. Without their support, this series would not be possible. And thanks to you for joining us. I'm John K. Waters, Editor-in-Chief in the Converge 360 Group of 1105 Media, publisher of the enormously popular Redmond magazine, among other tech trade tomes, and I'll be your moderator. Today's topic is automating DevOps best practices for enterprises. And our main speaker is the inimitable Howard M. Cohen. But before we get started, a bit of housekeeping. This episode is being recorded for later access. Keep an eye out for an email with a link to that recording. It'll be coming your way in the next few days. We'll make some time during the talk for some questions. Feel free to type your questions into the Q&A box at any time. We'll do our very best to get to all of them. Our sponsor, Quali, has provided some extra resources that can be found on the right-hand side of your screen. Be sure to check those out. And as a small thank you to all the attendees who stick with us to the end, we'll be sending you a $5 gift certificate to Starbucks. It's a cup of joe to go with the info. Now let's meet our main speaker, technologist, content creator, and senior resultant, Howard M. Cohen. In his 40-plus years in the IT industry, Howard has held senior executive positions in many of the top channel partner organizations, and he currently writes for and about IT and the IT channel. Howard is a sought-after speaker, an insightful observer of the technology landscape, and one of our very favorite presenters. Take it away, Howard.
Well, thank you for that beautiful introduction, John, and I still love that cup of joe to go with the info. Ho, ho, ho. Okay. Hello, everybody. We're here to talk about automating DevOps, and what I'd like to start off with, as I always do, is a word of the day. Today's word is continuous. It's continued on the next page. We kind of slipped off the side there. I'm sorry. But it is continuous. I guess it could have been perpetual, given that this is a perpetual motion machine. But continuous means that it's constantly happening, more and more and more. It doesn't stop. And everything we're talking about today, the goal is to create something continuous. In this case, it's continuous improvement. Continuous improvement of our software, the software our people use, and continuous improvement of the products that software supports. And we achieve this continuous improvement through the continuous development, delivery, and deployment of software. That's what DevOps is really here to help you do. Let's take a look at a simple sequence, the simple sequence of DevOps. It begins with a development group creating new code. They create an application, something, get to work right away. They then release it to the ops group, the operations group, who deploys that new code. They put it on their systems and make it work and make it ready for users. Notice, development, DevOps, there it is. Next, we get to the users who use this program. As soon as they start using it, the ops people jump back in, collect feedback from the users, and bring it back to dev. And what do? The same thing it says there on the arrow. Create new code. They create an upgrade, an improvement, a new iteration of the software, release it to the ops group who deploys the new code. The users then start using this new and improved program, and you guessed it, ops comes right back to them to ask them, how's it going? How do you like the software? What would you like us to change? And then, of course, they bring that back to dev, and, well, you know what dev does next, and it goes around and around and around and around. What's important to grasp, though, is that this cycle occurs dozens of times per day in some organizations. In fact, some organizations have new iterations of their software hundreds of times per day. So this is very quick, very, simple improvements, but they're happening continuously. For a user who used to sit there and go, gee, I wish it did this, this is the ideal environment. Because when you say, gee, I wish it did that to the ops people, they give it to the dev people, and guess what? Next time around, it does that. So that's really the heart of what DevOps is. DevOps occurs in an environment that begins with a network, as does everything. That network connects together a wide variety of resources. Each of those resources runs on some kind of operating system, and there's nothing that says that they all have to run on the same. This is an open environment, and different users with different operating systems can indeed be involved in a DevOps system. And it consists of orchestration, some agent that makes sure that everything is where it needs to be, when it needs to be there, and everybody's got what they need to do what they need to do. So we've got a cycle that happens in an environment. And it happens on a platform. We're going to talk about the DevOps platform. What's needed for you to be able to efficiently run a DevOps operation? Now, here's the good news. Everything you're going to see here in this segment is an opportunity to automate. There's ways to automate almost every step of this. Let's start with open systems, which really is a vehicle for automation in many ways. It provides open standards. One of the joys of an open standard is that everybody can ultimately agree to change one if they feel the need to. So there's flexibility built in, but there's still the structure of standards. It provides for packaging of your software. This basically refers to cloud-native software. For those of you who are unfamiliar with the term, all the software we used to write going back into antiquity when I got started is now referred to as monolithic. Monolithic because it's basically one big block of code. Everything you need to do for the program to do its job is in that block of code. And of course, if anything fails in there, everything comes down. And that's a weakness. Today, we use microservices that are in containers. The microservice is one thing that was in that block of code. It's one service, one thing that happens with the software. And every time the operation needs one, it requests it. That service is instantiated. It's packaged in a container along with all the resources it needs to run, and it's transported to wherever it needs to be on the network platform. That's why it's referred to as cloud native. It is ideal for use in a cloud environment where you need to transport things all over the place, quickly, all the time. So there are terrific tools to help you package your microservices into containers with all the resources they need and make them ready for use. Runtime engines make it possible when those microservices arrive where they're going, the runtime engine runs them. They're executable modules, and something's got to execute them. That's runtime. And there again, all the work that a runtime engine does can be automated. Configuration. From time to time, you need to change configuration to accommodate new additions. There again, it can be identified that configuration changes are needed, and the configuration changes can be automated. We know that networking is highly automated these days. Much of what we used to have to do manually is taken care of for us automatically now. Storage, especially software-defined storage, can be automated, assigning where something's going to be stored, how many pieces it's going to be broken up into to protect it, how many copies are going to be made. Where is it needed most so we can put it in the storage facility closest to those users? All of this can be automated. Orchestration, as we talked about before, putting everything where it needs to be when it needs to be there, is automated. And finally, resource management. If we didn't automate resource management, there could be no cloud computing. The heart of cloud computing is that a user can sit at a self-service console and request the things that they want, and they're provisioned for them automatically. More memory, more storage, more processing power, whatever they need, automatically provided. Talking about a CI/CD pipeline, this is a continuous delivery pipeline. It's all the things that are being talked about that we may add later when we have time. It's also some of the things that we can't do yet because other things will have to be done first. In an environment where we're quickly getting feedback and trying to make changes based on it, we still do need to have a structure for moving forward. And so a CI/CD pipeline is helpful there. And getting things onto that pipeline can be automated. Provisioning, as we spoke a moment ago about, can be automated. It is automated by the nature of cloud computing. You go to a self-service console and you get the resources you need. Capacity. You don't have to sit there with just 2 terabytes of storage. If you're now using more, you can just request a 3rd terabyte or a 1/2 terabyte or a number of gigabytes. You can scale your storage to your need very automatically. And with no manual intervention. Your request does not go to a person. I am the great and powerful Oz. No, there's nothing like that. It's done for you purely through systems with no people having to give up time to take that or waste time waiting for them. This means we can deliver apps faster. Everything we need to do to deliver apps is automated. And so there are very few things we need to do to start a new release. One of the biggest advantages that people are jumping into as an automated advantage is the concept of infrastructure as code. This basically involves automatic infrastructure provisioning. What does that mean? I'll take you back again in the Wayback Machine to the days when I was young in this system, and if we decided we needed some new infrastructure to support a new application, we went out and we looked for a new server, and we shopped for storage, and everything we needed in between. We constructed a purchase order, sent it out, got the equipment shipped in, we assembled it, tested it, installed it, integrated it. All of that took months. So the time from idea to implementation was months. Today, or yesterday, a user could simply say, well, let's see, I need a server. So they basically order up a new virtual machine, a new VM. Say, I need this much processing power, this much memory, this much storage. It needs to be this fast. It needs to be this large. And that infrastructure was created for them. Infrastructure as code takes this even further. Basically, we describe all of what I just talked about, all of the memory and storage. We describe everything about the infrastructure we need and create it in code. When we need a new one of that infrastructure, we simply call up that code, and it does all the provisioning for us. So we're basically automating the automation, taking it even further. This means that you can create new environments for testing, for development, for whatever you need. You can create new environments without getting anybody involved. You simply construct a piece of code to do it, or you have that constructed, and you run it whenever you need that infrastructure. This also simplifies scaling. Think about this. One of the things we worry about most is when the organization gets bigger and has bigger needs, how are we going to make our systems keep step with that? How are we going to make them get bigger along with the requirements of the organization? Here's a simple answer. Every time we need a new server, a new VM, we can configure it with everything that it needs to function, and we can establish that as a very simple piece of code, run it when we need it. We can scale up, we can scale out, we can scale any way we need to scale, and very simply, by calling up that piece of code. So it makes it even easier for users to get more functionality without impeding anybody else's time. I did want to stop and talk about log management and about collecting logs. There are many people to this day who still leave their logs switched off. And I can't imagine why they do that. See, here's the thing. I was writing this the other day about logging. If you want to be able to explore or research anything that happened, well, you have to capture everything that happened. Because how do you know what to collect? How do you know what to capture? Logs capture everything. And so you can go back and interrogate those logs and find what you were looking for. Come to understand why something went wrong, for example. Find out the root cause of a problem and perhaps solve the cause and keep the problem from ever coming back again. So we strongly recommend that you turn on all your logs and make sure that they're kept. Make sure that they're aggregating all the new data and keeping it together so you can examine it anytime that you need to and see the picture in toto. The data has to be parsed in many ways often. You need to interpolate and extrapolate, and you need to organize it in such a way that you can see the data more meaningfully. And then you finally get to perform analytics with the data, which should result in usable information, answers to questions. The other thing to worry about, because logs get big, there's a lot of data going in there, you need to worry about having storage available for those logs. This storage doesn't have to stay online for long. You should set up a schedule in which you archive the data that has gotten past a certain age. The other thing you must make sure you do is secure your data and make sure that it's compliant with any regulations that you may be subject to. Log data from a network, from a server, from any of the things that are involved in this environment, those are sought after, beautiful, wonderful resources for bad actors. If somebody wants to get into your network, the best way to learn more about it is to interrogate your logs and see what's going on your network. You want to make sure this data does not fall into the wrong hands. So the focus you put on securing it, the automation you put into securing your log data is critical. I know I spent a lot of time on logs, but this is important. I've seen environments where something went wrong, and we came in to fix it, and there was no fixing it. We had no way to know why it went the way that it went. This is something you can protect yourself from. So plan out and organize how you're going to collect your logs, when you're going to archive them, and how you're going to keep them totally secure. A final part of the DevOps platform is a unified tool chain. Now, I'm going to admit to you that the word tool chain is becoming outmoded. It suggests a chain of tools. Today, we're suggesting that you prefer best of platform instead of best of breed tools, and by doing so, eliminate point solutions because that's what those tools are. Each one is a point solution. It takes care of one thing. Now, engineers love those tools. You get to using the tool, you get to knowing the tool, you want to use that tool. It makes a lot of sense. But what happens when somebody else has to pick up where you left off? What happens when multiple people have to work on the same thing and they're all using different tools? What happens when the next thing you need to do is connected to the thing you just did and the two tools don't work together? Far better to implement a platform of tools, a platform of services to do everything you need to do in your network environment. First of all, they're designed to work together. Second of all, they share a common user interface. What does this mean? First of all, it simplifies training. When you only have to train on one user interface rather than dozens upon dozens of user interfaces, an automated platform becomes far simpler. You can get everybody up to speed quickly. When you have new people join the team, they just have to learn that one interface, and they become useful. They can bring value much more quickly than ever before. It also simplifies support. If you've got 15, 20 different tools, you may be talking to any of 15 or 20 different support organizations. And there's inconsistency between them. Some are better than others. Some are far worse than others. It's a crapshoot. And so you don't want to roll those dice. You'd prefer to have a platform from a platform provider who is well-resourced and has everything you need to help you when you need that help. All of this leads to one very important word, and that word is interoperable. Ever since the institution of the Internet of Things, everybody has vividly seen the importance of keeping everything interoperable. You're not going to have hardware components from the same manufacturer. You're not going to have software components from the same developer. You're going to mix them. They're going to have to work with each other, which means they must be interoperable. Let's begin with the tools we use to manage them. If those tools are interoperable, we can stay focused on keeping everything, and I mean everything, interoperable. Okay, earlier we took a look at the cycle that DevOps generally moves in. Of course, there are formal steps, formal stages, if you will, in that cycle. And what I'd like to do now is to look at how these things used to be done and how we're doing them now in a DevOps environment that is far more automatable. Let's start with planning. Planning used to begin with an assessment of the business requirements. And by the way, it still does. Everything is about creating better outcomes for businesses. So that would take some conferences and some discussions and some documents to be drawn up and approved, and that could take some time. We usually developed a functional spec. What exactly is this program going to do? And I mean, what is everything it's going to do? We had to go from top to bottom, all the functionalities that should be present when the application is finally constructed. Once we had all of that in place, we used it to help us craft a release plan and a schedule of releases. So if we could release it in phases, which wasn't always the case, we could release it in phases. Often, we had to release the entire monolith at once, and that engendered tremendous delay. Phases were great, seldom. And of course, planning for governance. How are we going to measure how well it's performing? Ultimately, all of this culminated in a roadmap that could be shared with everybody involved in the application. And so we all kind of tracked that roadmap going forward. New revisions came out every few weeks. New versions came out every few months. That's how monolithic software went. Now, of course, we're in the age of automatable DevOps. We start off with a mind map. We chart out all the things we'd like to do right away, and maybe some things we'd like to do later, but what we want to know is what is the quickest usable product we can develop so that we can get it into operation right away and get our people started creating value. We then set up a Kanban table so that everybody can keep track of where they are in doing what they're doing, and everybody can see where everybody else is. It becomes very simple, very fluid. We use this to automate our calendaring so that everybody knows what to expect and when to expect it. Collaboration is as automated as it has ever been. We can reach each other with a click. We can go from texting to voice to video, whiteboarding, application sharing, document editing simultaneously. We have all these wonderful automated tools to help everybody get together and agree on the things we need to agree upon and communicate whatever else needs to be communicated between each other. So the planning stage has gone from a very long and drawn-out process to a very quick process with very, very short-term goals. Coding. All right, we have a functional spec. Let's start coding the application. That involved the development of code. And since it was a large piece of software, we had different people working on different sections of it and having to make sure that they were aware of all the configuration artifacts that they would have to share, and they would have to maintain contiguity between what they were doing and what everybody else was doing. And often this was a source of tremendous delay. On a regular basis, we'd have to take everything together, review it all, to make sure we're all moving in the right direction and we're getting the job done. We would probably have to get involved with some significant change management because there would definitely need to be changes made to what we were doing. And as we started to get closer to release, as we were doing test versions and whatnot, we started to involve our versioning so that we could keep track of what version we're actually up to. And if necessary, we could roll back to previous versions if the situation warranted. If that all sounds very time-consuming, it's because it was. It's very time-consuming, and that's why we set very long, very large time frames for the introduction of anything. Today, we start with prototyping tools to figure out how we're going to do what we want to do. Everything we do is sent into a source code repository that only the right people can access, but it's people who are responsible for every stage of the development of the software can get in there and do what they need to do. Given that there are so many people getting in there, we have to make sure that they can check things out so that nobody else modifies them while they're checked out, and check them back in when they're available again so other people can do what they need to do. Here, we're not working on different segments of a large body of software. We're each working on microservices that are completely separate and apart from all the other microservices. They're called up to do what they do it, and then they're gone. So there is less need for tracking contiguity between them, connection between them. There are also a lot of tools now, automated tools we can use to review the code, to make sure that it's correct, that the syntax is correct, that it does what we expect it to do, that it's optimized for best performance. Tools for all of this testing are available to us to test everything on an automated basis. So the process of actually coding something, coding a microservice, it's very quick. It's very quick. If it weren't, we couldn't be doing this hundreds of times per day. Then, finally, when we have our microservices all built, it's time to build the application so that it can call all the microservices as it needs to. In the old days, we would compile all of our source code into executables. Executables are large, they're vulnerable, they can easily be damaged, corrupted, if you will. We did code quality testing pretty manually. We then went out and did performance testing to see how well they were functioning. We provided documentation so that everybody knew how to use what we were talking about. Today, we go right into the source code repositories. We have a build engine that reaches in, takes all the microservices it needs, and builds the application. Everything's ready to rock. We have automated testing tools to do all of our testing, and off we go. As far as the testing goes, in the old days, we had to manage quality for production. We did a lot of Six Sigma stuff, trying to make sure we were documenting all of our processes and adhering to quality best practices and so forth. We then did unit testing of the entire software unit, which was followed by acceptance testing. Here, we would send out something to the users to test, a pilot, if you will. And they would test it, put it through its paces, and come back to us and tell us whether or not it was working the way it was supposed to. If not, we had to revise it and go through the whole process again. If so, we could move forward. We would then do regression testing, and finally, we would move on. Today, we live with automated self-testing. As soon as we've written a microservice, as soon as we've written any piece of code, we can submit it to the engine for quick automated testing to make sure it works. As far as acceptance testing goes, what we used to call acceptance testing in the old days, we now call deployment. When the operations people take the software that the development people have released, they simply deploy it, and the users use it. That use of it is really today's version of acceptance testing. They're using it in vitro, out there in the field. It's in production. And if it's not working, boy, we're going to go through that next iteration as fast as we can. So the automated self-testing gets us as far as it can. Users using it tell us, I didn't like this, or that's not working. That's not how this is supposed to work. And the ops people bring that back to the developers, who then create the next iteration to improve upon that. I keep mentioning that the developers release versions to the operations people. In the old days, that started with staging. We would stage the software, make sure that everything was working, make sure that we created a complete package for it so that we could then put it out to where it was needed. If there were multiple features, we'd have to coordinate with the developers of the other features to make sure our features worked together properly. Again, very time-consuming. Today, the orchestration engine simply puts everything where it needs to be. It automates the schedule of the release, and the operations people make sure that everybody gets the software they're supposed to get, and off we go. So software releases are easy. Software deployment, same thing. We used to have to make configuration adjustments wherever necessary to accommodate new software. We'd have to optimize the network from time to time because the new software did things the old software didn't do. We'd have to re-provision storage in many cases because the new software maybe generates more data that has to be held. We'd also have to change the network in some cases to support more data passing through the network. All of these things would have to be adjusted, usually pretty manually. Today, we use infrastructure as code. It goes out and does what needs to be done, reconfiguring storage and network, optimizing everything just the way we planned at the run of a simple routine. Configuration of everything, automated. Provisioning, automated. So it all happens without user intervention. And then finally, we get to monitoring. And we've always had performance monitoring. We've always had security monitoring to make sure that all of our security provisions work. We've had monitoring of the infrastructure to make sure that all of the long circuits work. And we were all very concerned about managing the user experience. That has not changed. The way we used to do it was much larger, required many more operators sitting at consoles waiting for lights to turn red. Today, once again, we use infrastructure as code. And since configuration and provisioning are all automated, most of the monitoring that takes place occurs with the setting of thresholds and the alerting that they've been exceeded. And that's the only time that an operator really needs to get involved. Otherwise, most of monitoring is automated. We'll get back to monitoring in just a minute. We said at the beginning that we were going to talk about best practices, and indeed, everything we've reviewed regards, this is best practices for DevOps. This is best practices for how we create and grow applications. Applications are living things now. They live and they grow with us. And that's why they're so much better received than ever before. The best practices I want to make sure you walk away focused on start with open source. Using open source platforms, open source tools gives you access to the entire consortium, the entire community of open source developers. This gives you much more flexibility in fashioning the tools or modifying the tools you need to exactly the purpose you have for them. When you're creating code, one of the best practices is have an eye toward the future. Try as much as possible to use publicly available variables, to have everything declared so that it's accessible to anything else you may write, and write code that you can reuse for other purposes. Try to keep to standardized structures. Developers know a lot of tricks to create something they can cut and paste into a new piece of code from an old piece of code to accelerate their ability to create more code. The more you can do this, the better off you are. We talked extensively about tools, and once again, you want tools that are integrated into a platform, that are all in the same toolbox, if you will, from the same tool forge, if you will, because they were built to work together. They were built so that people who could use one can use the others. The user interface is consistent between them. So prefer integrated tools. Also, OS agnostic tools. Operating systems, you may be servicing many. Your tools should not care. Your tools should be able to create effects that can be accessed and utilized and taken advantage of by any user with any reasonable operating system. And finally, and I don't think I emphasized this enough in the presentation, but measure everything. I talked about keeping the logs on. Whatever you can measure, do measure. Over time, you may find that there are things you're measuring that you're never going to use. Better you waste a little time up front measuring something useless and then just switch it off when you know it's useless. Then you turn around and say, oh, I wish I'd measured that. You know, you cannot manage what you cannot measure or did not measure. Famous words from Peter Drucker. If you're going to manage it, measure it. And with that, John, do we have any questions?
Thanks, Howard. Yeah, we actually do. And we want to remind everybody that you can still type your questions into the Q&A box at any time. Let's go. Our first question is from, I'm going to get this wrong, Savaram. Can you give us some examples or popular tools under each category of DevOps?
And I would love to. I cannot. Because this is a sponsored event, we have adopted a policy that says we never talk about specific projects. Specific products. during the Coffee Talk sessions.
Gotcha.
These are clearly available to you in most of the related publications. You can certainly go to the Open Source Consortium. They can give you all kinds of products that can do all kinds of things. And the most popular ones, you'll recognize the names because they've been out there. But yeah, I appreciate the question, but it's against policy. So
okay, here's one from, totally understood. Okay, here's one from Anna. She's wondering, Howard, can DevOps automation be applied to monolithic applications if you're still writing them?
Given that part of the DevOps process depends upon the division of labor created by microservices, I don't know exactly how. I suppose it could be done physically, but I can't imagine it being practical.
Right.
It's just too much involved in modifying monolithic software. There's too much that you have to analyze and look at, because everything you change can result in unanticipated changes down the road. So I would say, for me, I wouldn't do it.
Gotcha. Okay, here's one from Key. He's wondering, are you saying monoliths can break, but microservices cannot?
No, I didn't say that at all. What I said was that if anything breaks in a monolith, the entire thing can come down. Compare that to the way that microservices work. When the program needs a microservice, it requests it. The microservice is then instantiated automatically. It is packaged in its container with all the necessary resources automatically. Now, any one of those microservices could somehow be malformed. Something was missed. Something didn't make it. It is definitely possible to have a broken microservice. That's immediately identified. The microservice in question is then thrown out, discarded, gone, bye, see ya, and reinstantiated. Users never know that occurred. Nobody ever knows that occurred, and the entire operation just continues humming on. So, yeah, microservices can break, but one of the reasons that cloud-native software is so far more resilient than monoliths is because if something breaks, who cares? Throw it out, get another. That's, it's a beautiful thing.
So how about security in DevOps? We have a question here about, what is it and how it evolved. So I guess it's DevSecOps.
Well, yeah, the evolution has been called DevSecOps, basically, and I don't know why it didn't start there. I think that was an oversight on some people's part. Security, in many ways, is not very different because you're still transporting data over a network. So all the rules apply. All the data is formed in packets. Those packets get to be inspected. They get to be checked and tested. And they get to be monitored to see if there's anything that doesn't belong. All the things you would do in a typical security stack, you would do in a cloud-native security stack. One of the things I point out all the time, the International Standards Organization gave us a wonderful open systems interconnect model, the 7-layer model, if you will. And whenever I show off that model, people ask me, well, where's the security layer? There is no security layer. And it's true. There is no security layer, because my answer to that question is yes. In other words, the security layer is at every layer. Every layer has to have security provisions. That doesn't change just because you move to cloud-native software development. So, the security team still does the job it has always done.